Hi, and welcome to this VisionPack summary video, as well as a quick GStreamer demo. So first of all, what is VisionPack? So VisionPack is a vision machine learning SDK that provides middleware and integration with frameworks such as GStreamer, OpenCV, and Qt, as well as low-level C, C++, and Python APIs for integration into custom frameworks, and integration with DeepView RT and the vision pipeline, so camera, ISP, and GPU integration. So if we look at a typical vision pipeline, there's capture, image processing, inference, output processing, and then analysis. So looking at all of these, so here VisionPack provides production-ready reference applications that demonstrate end-to-end implementations. They are packaged either as base applications integrated with Yocto or using custom packaging, or integrated into Docker containers or multi-container orchestrated. Camera interfacing can be done with Video for Linux, libcamera, GStreamer, or for higher level APIs such as OpenCV, or using Python for GStreamer and again OpenCV. The image processing is a part where there's special optimizations. They provide zero copy into DeepView RT, leveraging NPU backdoors for DMA to really minimize this input processing time, as well as convenience functions for various scaling, crop, conversion, and normalization. Inferencing at its core is provided by the state-of-the-art DeepView RT inference engine, though integrations are also provided into different frameworks to make it seamless to integrate with GStreamer, OpenCV, or Qt while working with DeepView RT. Reference applications are provided showing these different types of integrations and filling use cases such as classification, detection, pose, and others continue to be added all the time. For the output processing, provide optimized model decoders, specifically YOLO, CenterNet, and SSD optimized decoders provide best performance for getting bounding boxes out of the models. These model decoders are hand optimized and ensure that they will be correctly quantized and work well with the models. Finally, for analysis, the reference applications demonstrate cloud connectors, local data streams, accelerated overlays, and all these are packaged through well-documented reference applications, allowing you to use these models quickly and effectively. So that was a typical ML pipeline. A Dockerized version of the ML pipeline, where it might be split across a number of containers, each focused on its specific case. For example, the camera capture or capture from a video file or remote stream can be isolated in one container, providing video frames generically to the inference container, which handles the model, image pre-processing, and output processing. And then finally, a container that's in charge of managing the user application, and whether that's analysis or user observable overlays. The way this is enabled is through the video stream library, which provides an IPC mechanism sharing the hardware DMA buffers between the containers. This gives you a zero copy interface for distributing your video pipelines, whether GStreamer or using other frameworks. Next, we'll show some examples on how this is put together. Before this, I wanted to point out resources on the DeepView ML support site, which provides many documented examples, an extensive knowledge base, and numerous models and data sets available for EIQ portal. Now onto the GStreamer demo. So first we'll show a detection example on the command line, moving on to the C API, then measuring pipeline latency, showing how an application can be adapted for cross-process, and finally some performance comparisons to alternatives. So first of all, the GStreamer API is very straightforward, simple syntax with no magic parameters. This example shows one such example pipeline, which renders bounding box overlays to the screen from a camera feed. So the model parameters are automatically discovered. The user only needs to provide a model and the preferred engine, whether it be NPU, GPU, or CPU. The box decoding algorithms are automatically configured, so whether this model is based on SSD, YOLO, or CenterNet, or otherwise, the box decoding and model parameters get configured simply by requesting them on the command line. Now, we mentioned SSD, YOLO, and CenterNet, but others continue to be added, as well as examples for other domains that are not object detection. Now, adapting to C API is very straightforward. First of all, we follow just the standard GStreamer API. So for example, you only need to include the standard GSD and video headers for this detection examples. We use the existing GStreamer data structures for bounding boxes to encode our model bounding box outputs. They're extended to carry items such as the label and the score, and then the region of interest itself can be done using the GSD video region of interest meta. Now, this is important because by closely following GStreamer conventions means interop into Python or other languages requires no additional effort, and we leverage familiarity with GStreamer while adding support for inferencing. Now, pipeline latency can be done by measuring or capturing timestamps at each step of the pipeline. So in this example, we'll show that we measured this through a GSD pad probe, where each buffer event on the elements along the pipeline go into a buffer event callback, which records the time. So here we show that output in text form with a MobileNet SSD example. We can see that the overhead feeding a 720p frame into a model running at 320 by 320 and performing the bounding box decoding has very low overhead. In fact, in this example, while the demo is limited by the camera running at 30 frames per second, we can see that over 60 frames per second would be easily achievable. Now, cross-process pipelines are also a useful feature, and it's easily achieved using the video stream library, which is part of VisionPack. So we'll show a quick command line example. Now, video stream can work from C APIs, from Python. It also includes GStreamer pipeline or GStreamer plugin, which would allow you to mix a pipeline that could start in GStreamer, go through a native application, back into GStreamer, and mix and match. The mixing matching can be between different processes or different containers. So here we create the VSL sync side of it. So we capture from the camera device at 1080p and then save frames into the camera socket. And then the second process pulls frames out of the camera socket, runs them through DeepView RT, and then into an app sync to process the results. Now we show this application running with that top output, and we can see CPU load is very low while passing 1080p frames around. And this processing includes the IPC of the frame passing as well as running the DeepView RT. So this allows applications to be better modularized, improving maintainability, security, and functionality. Now, to compare VisionPack performance against another similar framework for, as far as GStreamer is concerned, is NNStreamer. It's important to keep in mind other advantages are integration into other frameworks. It's not limited to GStreamer, even though that's a popular framework. There's integration for OpenCV, Qt, and the low-level C API makes it easy to integrate into other custom frameworks, including some just using standard low-level Linux system libraries. It provides the inter-process and inter-container vision pipelines, as well as well-documented reference applications and commercial support. For the performance comparison, we'll be comparing two MobileNet SSD models. So first at 320 by 320, we can see that the VisionPack pipeline is almost half the processing time. And then when we go up to a 640 by 640 pipeline, so as the vision pipeline becomes more dominant, we can see the savings continues to increase. So this shows the performance benefit of the VisionPack. Going beyond that, advanced models, VisionPack allows you to go further than just SSD models in your vision pipeline with models such as CenterNet and YOLO. Now, the reason why these models are important is they provide roughly twice the accuracy as an SSD detection model while maintaining equal performance windows when using the VisionPack for capturing times. Models such as this are also available as part of ModelPack, allowing you to train your own advanced models using our optimized implementations that are especially optimized for the NPU and providing full quantization support while maintaining full precision. That concludes the quick GStreamer example. What's next? So beyond showing more different types of applications that can be put together with this framework, we'll also have more examples using OpenCV, some Python examples using GStreamer, using OpenCV, showing how to take standard NumPy type code and interact with the camera and DeepView RT, as well as some Qt examples that bring in all these DMA advantages into sort of a typical custom GUI application. That's it for today. Thank you for watching.